Having spent some time discussing basic notions of financial mathematics, we'll now move on to the more complicated notion of interest. This can be thought of as the amount of money paid by a borrower to a lender. So think of it as if you keep your money in the bank, you're allowing the bank to borrow your money, which it will then use for its financial transactions like mortgages. So it's borrowing money from its depositors in order to make a profit. So they pay their money to you. They pay you a small fee called their interest. This notion extends to many other types of financial transactions. We don't study which transactions have interest and what kind of interest. We think of them purely on mathematical grounds. We'll introduce two different models of computing interest and study how they differ. We'll start with, simple interest. Of course, it is simpler than the one which will come next. To do this, all you have to do is say, take your initial amount of money, called your principal, and multiply it by the rate of interest, R, which is typically a per year rate, and then also multiply by the amount of time you allow the borrower to hold your money. So I say, take my initial amount, my principal, and for every year that I let you hold my money, you pay me the rate R. So I multiply P times R times the number of years. And this tells me the amount of money I earn as interest. So the total amount of money that I have is equal to what I started with plus the interest I've accrued, which can be written in a compact way as P times 1 plus RT. Sometimes this is a helpful way to think about interest, but this is only if you're interested in the total amount of money you've acquired, which is to say your principal plus your earned interest. So let's look at a few examples. So for each of these, we have a principal amount, an effective rate, and a time for which the interest will be computed. And what we will do is compute the amount of interest earned. So we simply follow the formula, which is I equals P times R times T. So here I is equal to 10,000, my principal, times my rate is 3.1%, so times 0.031 times 5 years tells me the amount of interest I'll earn in that time. It's about $1,550. In the next example, we have a higher rate, 7.3%, but a much smaller amount of time. So 0.037 is the rate, but I only hold for 6 months. So I don't multiply by 6, I multiply by 0.05 because this is equal to 0.5 years. So I compute this and I get $200.75. So here we have a long-term loan at a very high interest rate. The 18% is quite high. You would not want to be the borrower in this case. You would want to be the lender. Because let's look how much interest is going to be paid off of this. Follow this out, and I get $1,800. So even though the principal amount was only $1,000, because the interest rate was so high, it was 18%, and the loan was so long, I pay almost double the principal just in interest. So in this case, you would definitely want to be the person lending the money because you would be accruing a great return on your investment. And if you were the person who borrowed, well, you got $1,000, you were allowed to borrow that, but you paid $1,800 for that privilege. So not a very good deal for the most part. In the last example, we get to see that even if you have a big principal, 100,000. The interest rate is extremely low here. It's 0.1%, which means 0.001 is what we multiply by for R times 10. So only $1,000. So even after lending $100,000 for 10 years, the only interest you get back is $1,000. So this is what happens when there's very low interest rates, which is what's currently happening in the early 2017, late 2016 markets. A lot of interest rates are very low, so you can't really make very much off of these things. You have to look for other investments. Okay? A more interesting notion of interest is what's called compound interest. So how does this differ from simple interest? Well, what compound interest says is, in reality, when I make a loan to somebody, they pay me interest, but they don't pay it all at the end. They pay it, say, every year or every month. And then they pay interest on that interest, right? So it allows me to, say, collect interest on the interest I'm collecting iteratively instead of all at the end. So the key point is that the interest is paid not just on the principal, but on the interest accrued over time. So in general, the amount that you earn from compound interest is somewhat greater than the amount you earn from simple interest, because I'm allowed to collect interest on interest. So what is the formula here? I mean, we will not go into the derivation of this formula. It's usually taken as a given in introductory courses, though it's not incredibly difficult to derive. The value of your investment will be the principal times this quantity 1 plus r over n to the nt, where here n is the number of times the interest is, where essentially how often do we collect interest on the interest. This is called the compounding rate. Okay, so for example, if we say we compound after every year, this would say I'm going to pay interest at the end of the year on my interest. This would tell me that n is equal to 1. If I'm going to compound, say, daily, so at the end of every day I pay interest on the interest I've earned, then n is, let's say, 365, except for a leap year. That'd be 366. Let's look at a few examples of this. Before that, though, we should think about an interesting question, which is, how often should I compound? What is optimal for me as a lender? Well, should I compound once a year? Should I compound at the end of every day? Should I compound every second? Does it matter very much? Well, there is a notion called compounding continuously, or continuous compounding, where I compound at every time instant. So I'm always iteratively collecting interest on my interest. How is this justified mathematically? It's with taking n to infinity. So this can be made precise with the limit notion from calculus. So we will not get into that until you get to calculus. But one can show that under this model, the amount is computed actually in an even simpler formula. It's computed via the famous PERT formula, P-E-R-T, where again, P is the principal, R is the rate per year, and T is time. And you might recall from our earlier modules, we have this nice constant E, which is Euler's constant. So I mentioned in the earlier modules that Euler's constant seems to have a penchant for appearing in many different circumstances, and this is one of them. Sort of out of nowhere, it becomes the relevant base for a model for interest. I mean, it's really a beautiful thing that this sort of strange mathematical concept just appears out of nothing. But for us, we take it as a given. So what we'll do now is look at a few different situations for compound interest. So here we have $1,000. The interest rate is 4.5%. We'll lend for 3 years and compound annually. Okay, so what's our formula? I take the principal of 1,000 and I multiply by 1 plus the rate, which is 0.04. The number of times I compound is just 1. I go for 3 years, so 1 times 3. And this is 1,141.17. Now we'll look at a succession of examples where I am gradually increasing the rate of compounding. So I'll fix the principal, I'll fix the rate, and then I'll go from quarterly compounding to daily compounding to continuous compounding to see how much it matters. So here's 3,000. The rate is 0.075. I compound quarterly, so I divide by 4. And then I have n is 4, t is 1. So this is 3,231.41. Make a nice little bit of interest there. Here, I've kept everything the same, except now I'm compounding daily. So the amount is equal to 3,000 times 1 plus 0.075. Now I divide by 365, which is bad for me if I'm the lender, but I get the benefit of having a larger exponent. Now it's 365 times 1, and this is something like 3,233.63. So I went from compounding once every season, once every 4 months, to compounding daily. And how much benefit did I get? $2. Not very much on a $3,000 principal. So this indicates that maybe there's not such a great gain from compounding at very rapid rates. In fact, if we allow the rate to go to infinity, that is, I'm compounding every time instant, we can see exactly what the best I can hope for is. In this case, we follow the PERT model, so 3,000 times E. The rate is 0.075, and this is equal to 3,233.65. Okay, so let's just compare the difference between compounding daily and compounding continuously. It's 0.02, so 2 cents is what I get for going from compounding every day to compounding continuously. So what this tells us is that there's a limit of how much bonus I can get from doing this compounding. I can't sort of somehow accrue infinite wealth by constantly collecting interest on my interest. There's a limit, and it's given by the PERT model. So again, let's look at an example where I have a fixed principal of 1,000, a fixed rate of 5%, and a fixed time of 10 years. And I'll look at how much interest I earn, or what the total value of my investment or loan is, under the simple interest model, the model of compounding every month, and the model of compounding continuously. So for the simple, the total amount is the principal times 1 plus RT. So this is 1,000 times 1 plus 0.05 times 10, so 1,500. Basically, I make $50 every year for 10 years. Makes sense. So for compounding monthly, the model is A equals 1 plus R over N to the NT times P, of course. So P times 1,000 times 1 plus 0.05 divided by 12. 12 times 10, which is equal to about 1,647.01. So I definitely get a bonus from compounding my interest. I gain about $167 in interest. No, sorry, $147 in interest. But what is the benefit from compounding continuously versus monthly? We saw in the previous example there was minimal benefit to compounding continuously versus daily. So let's see if there's a big difference here. PERT is the model. So 1,000 times E to the rate of 0.05 times 10, which is approximately, 1,650, let's say. So really a very small increase. And this shows us that although there's a benefit to compounding versus following the simple interest model, there's not very much benefit to, say, compounding monthly versus compounding continuously unless you had a very high rate or very high principal.